Welcome back, ladies and gentlemen, to another exciting AP chemistry video. Today we are going to do our best to finish up some of the major components of Unit 1, and that is going to include us taking some time and working through periodic trends. That is, understanding things like atomic radius and ionization energy and electronegativity, and understanding how the principles of atomic structure play a role in those particular properties. So sit back, get something to drink, take some notes, I don't know, sneeze. Let's get going. So the learning objectives for this particular video: you should be able to explain the relationship between trends in atomic properties of elements and electronic structure. So we're really going to be looking at and trying to understand the organization of the periodic table and understand how that plays a role in understanding some of these fancy periodic trends like atomic radius and ionization energy. So the essential knowledge for this particular unit is as follows. The organization of the periodic table is based on the recurring properties of elements and explained by patterns of electron configuration. So if we go back and look at the electron configuration video, it gives us a better understanding of how these atoms are built on a molecular level, and understanding that atomic structure helps us understand the organization of the periodic table and the resulting trends of those as well. So we can really qualitatively understand the periodic table and the position of the element in the periodic table using Coulomb's law, shell model, and the concept of nuclear shielding to get a better understanding of those trends on the periodic table. These are going to be things like ionization energy, atomic and ionic radii, electron affinity, and electronegativity. So before we dive into any of that, I really want us to get a fundamental understanding of this concept here that is Coulomb's law. Coulomb's law is going to help you understand most of chemistry, to be perfectly honest. The force of attraction between charged particles is correlated to two specific things: the fact that like charges repel and opposite charges attract. And there's two factors that indicate the strength of the attraction. The first being the magnitude of the charge, that is, how big is the charge. So think if you have two weak magnets near each other, there'll be some level of attraction, but two larger magnets or stronger magnets are going to have a greater attraction to one another. Furthermore, the distance between the charges also plays a role in the attraction between the particles themselves. So if I have two magnets that are really, really close together, they're going to experience more attraction than two magnets that are really far away. Now, when we refer to charges, we need to think about the atomic structure. Keep in mind that protons are positively charged and electrons are negatively charged. So that's the type of and level of attraction we're focusing on when focusing on Coulomb's law in chemistry. I may use the term nuclear charge a couple of times in this video, and that just refers to the number of protons that are in the nucleus, roughly. There's a little bit more of a complicated explanation for it, but as long as you understand that nuclear charge refers to the magnitude of the charge of the nucleus, you should have no problem in understanding Coulomb's law and how it plays a role in some of these very important chemical properties. So let's have a quick discussion about the different types of electrons that are in an atom in and of itself. And there are two types. The inner electrons are called core electrons. Now, these are very, very difficult to remove. You can imagine that electrons that are closer to the nucleus are going to be more difficult to remove, and that outer electrons, or the outermost electrons, are going to be easier to remove. And so we refer to those outermost electrons as valence electrons. And as I mentioned before, the ease of the removal of an electron is based on the nuclear charge in Coulomb's law. So if we can imagine the electrons being further away from the nucleus, we can imagine that they're going to be easier to remove, and electrons that are closer to the nucleus are going to be more difficult to remove. It has to do with the attraction of those electrons to the nucleus. Remember that distance plays a huge role in the attraction of oppositely charged particles, and that's one of the big fundamental things of Coulomb's law. So the closer those electrons are to the nucleus, the harder they are to remove, and the further they are away, the easier they are to remove. Electrons further from the nucleus experience less nuclear charge, essentially less attraction to the nucleus due to their distance, and this makes those electrons easier to remove. So if you take a look here, you have three different atoms and their Bohr models. We have lithium, sodium, and potassium. The potassium electron is in an energy level that is further away from the nucleus and therefore experiences less attraction to the nucleus. Furthermore, nuclear shielding plays a role in this as well. As potassium's outermost energy level is further away from the nucleus, the inner electrons also shield the outermost electron from being attracted to the nucleus. Again, long story short, it just makes the electrons easier to remove from potassium than it is from sodium and lithium, due to the fact that their electrons are at a higher energy level and therefore are further away from the nucleus. It has to do with distance. So let's take a minute and evaluate this situation. I want to know which is more likely to lose an electron, sodium or potassium, and justify your answer. And justify it in terms of Coulomb's law. Well, I'm going to give you a minute to think about what we've just discussed. There's a real specific way I want you to go through and answer these types of questions. And then once you've gone through and done that, we'll go through, evaluate, and continue the rest of the video. We'll see you in just a moment. So as I mentioned before, there's a real specific way I want you to go through and answer this type of question. And again, we're looking at sodium versus potassium. Which is more likely to lose an electron? Well, if I look at potassium, its valence electrons are in the 4s sublevel. Sodium's electrons are in the 3s sublevel, and lithium's are in the 2s. So because the electrons in electrons in potassium are in a higher energy level, they are further away from the nucleus than that of the valence electrons in sodium. So I want you to make sure that you justify it like that. So I would say that K is more likely to lose an electron than sodium. The valence electrons, and I'm abbreviating for just the sake of the video, so I apologize if it's a little hard to understand, but the valence electrons in K are in a higher energy level than that of Na. Valence electrons in a higher energy level are less attracted to the nucleus and are easier to remove. Okay, so again, it's a pretty straightforward concept here, but as you work through this, I want you to think about claim evidence reasoning. State your claim. K is more likely to lose an electron than that of sodium. What's your evidence? Your evidence is rooted in Coulomb's law. The valence electrons in K are in a higher energy level than that of Na. Valence electrons in a higher energy level are less attracted to the nucleus and easier to remove. Okay, let's see what we got next. So what we've done here, at least for the very first one, is we've looked at what's easier to move an electron from in terms of elements that are in the same group on the periodic table, right? Everything that we just looked at, lithium, sodium, potassium, they're all in that first group on the periodic table. I'm only ever going to ask you to compare things either in the same group or across the same period. So things become a little bit different when we focus on Coulomb's law and across the same period, because those electrons are in the same energy level. We can't use the same justification as what we've done previously. So when we look at the same energy level, the required amount of energy to remove an electron increases. It becomes more difficult to remove an electron going left to right on the periodic table. Well, why? Well, it has to do with the fact that the number of protons increases in the nucleus going from left to right across a periodic table. So if I look at the second period, lithium has 3 valence electrons, beryllium has 4, etc. As we go left to right on the periodic table, the magnitude of charge of the nucleus increases. We have more positively charged protons. And as a result, the outermost electrons become more attracted to the nucleus due to the increased magnitude of the charge of the nucleus going from left to right on the periodic table. Again, if I look at the diagram here on the right-hand side, we can see that the number of protons increases going from left to right. That means that those outermost valence electrons are going to be more attracted to the nucleus due to the increased magnitude of charge of the nucleus going left to right on the periodic table. And as a result, because of that increased magnitude of charge in the nucleus, the electrons are harder to remove, right? More positive charge in the nucleus means those electrons are more attracted and therefore are more difficult to remove. Again, it's a simple concept that's just simply rooted in Coulomb's law. So we're going to utilize these ideas of Coulomb's law in order to describe a variety of periodic trends. And these are patterns that you see as you go either up or down a group on the periodic table or going left to right in a period on the periodic table. All of these trends are rooted primarily in Coulomb's law, so knowing it and knowing it well is very important. If you're comparing two things in the same group, I want you to focus on the valence electrons being in a different energy level, right? If I look at lithium's valence electrons, they're in the second energy level, whereas sodium's are in the third and potassium's are in the fourth. However, if we're going across a period, I want you to look at the increased magnitude of the charge of the nucleus. The number of positive charges in the nucleus increases, thus making the outermost electrons more attracted to the nucleus. And that impacts each and every one of these periodic trends. So we're going to spend a little time going through each one, understanding how Coulomb's law plays a role in each of these, before finally doing a little bit of claim evidence reasoning to evaluate each of these. So one of the first periodic trends that we are going to actually dive into today is ionization energy, and it goes back to what we've discussed previously about being able to remove an electron. Ionization energy is the amount of energy required to remove an electron. The trend of ionization energy decreases as you go down a group. This is due to the outer electron shells being further away and therefore less attracted to the nucleus, meaning that less energy is required to remove them. Again, when we go back and think about Coulomb's law, distance is one of the two big factors that plays a role in the attraction of the outermost electrons to the nucleus. If they are, on average, further away from the nucleus, they're going to be much easier to remove because they're less attracted to the nucleus in and of itself, thus resulting in a lower ionization energy. It doesn't require nearly as much energy to remove an electron from potassium than that of sodium or lithium because the electrons are further away from the nucleus. In addition to that, we can look at the trend going across a period in a very similar manner. But rather than looking at the distance from the electron and the nucleus, we can look at the magnitude of the charge of the nucleus. We have to keep in mind that in the same period, all of these electrons are in the same energy level. So we really can't focus on the distance aspect of those electrons being in a different or higher energy level. The trend of ionization energy increases going across a period. As the nuclear charge increases, since the valence electrons are in the same energy level, this results in greater attraction to the nucleus. The number of protons in the nucleus increases going left to right on the periodic table. And as a result, the outermost electrons are going to be more attracted to the nucleus that has the greater number of protons. You have to keep in mind, again, all the valence electrons here in the same period are in the same energy level. And as a result, the increased number of protons that are in the nucleus, the more attracted they're going to be to that nucleus and therefore require more energy to remove them. So you can take a look at this basic trend here. Let's take a look going from left to right across a group. As we start at lithium and go to beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, the ionization energy, or the energy needed to remove an electron, increases, and that's due to the fact that as you go across a period, the number of protons in the nucleus increases, resulting in those electrons being more attracted to the nucleus. However, if we look at the elements just at the bottom, so for example, like lithium, sodium, potassium, rubidium, and cesium, you can see the ionization energy goes down as we go down the alkali metal group. And that's due to the fact that the valence electrons are in a higher energy level as you go down a group. They're further away from the nucleus, less attracted to it, and therefore require less energy to remove them. You can see the same trend if we look at the noble gas group. Helium requires significantly more energy to remove an electron than that of neon, argon, krypton, xenon, and radon as we go down a group. Again, due to the fact that the valence electrons are in a higher energy level, further away from the nucleus, and require less energy to remove them. It's a bit tricky, but again, if you think about things in terms of Coulomb's law, you should be able to explain and justify these appropriately. Successive ionization energies play a big role as well. Second and third ionization energies are removal of more electrons. I want you to notice the large jump here. So let's look at sodium. Sodium's first ionization energy is 498 kilojoules per mole. The second ionization is 4,560, nearly 10 times higher than the ionization energy of the first one. Well, why is that the case? Well, once all the valence electrons are removed, core electrons are the next to be removed, which require much more energy to be removed. And based on this information, we can determine things like location on the periodic table. If I see a big jump between the first and second ionization energy, I know that that element is in the first group on the periodic table. This is a result of elements in that first group only having one valence electron, so one electron should be easy to remove, while subsequent electrons, core electrons, are going to require much more energy in order to remove them. Take a look at magnesium. The biggest jump in magnesium is between the second and third ionization. Well, magnesium is an element in the alkali earth metal group, the second group on the periodic table. And if I look at the electron configuration, it ends in S2, meaning that there are two valence electrons in magnesium that are very easy to remove, and subsequent ionization energies, or subsequent ionizations rather, are going to be removing core electrons. So based off of this information, I should be able to determine location on the periodic table as well as ion charge. The big jump in ionizations tells you how many valence electrons the element has. And remember that the number of valence electrons an element has is a periodic trend. The first group has 1 valence electron, second group has 2, and 3 through 8 if I look at the p block. So utilize this information to be able to figure out location of elements on the periodic table, their charges, and potentially what ratio of atoms they'll form when they form ionic bonds. It's a very, very useful tool when looking at ionization energies. Now, when we look at ionization energy, on the flip side of that, we can look at atomic radius and understand that justifications for atomic radius are going to be exactly the same as ionization energy, just in reverse. The more attracted an electron is to the nucleus, the smaller the atom is going to be. And it's the same going the opposite direction. The more attracted an electron is, the smaller it will be, and the less attracted, the further away it will be, or the largest radius. So notice as we go down a group, the radius increases, and that's due to the fact that the valence electrons are, on average, further away from the nucleus because they're in a higher energy level. And when we go left to right on the periodic table, for the most part, the radius decreases as a result of the valence electrons being more attracted to the nucleus as the increased magnitude of charge occurs going left to right on the periodic table. Now, when looking at ions, things are a little bit different. The radius of a cation, that is an ion that is positively charged, is usually smaller than that of the atom's radius in and of itself. And that's due to the fact that cations lose their valence electrons. And as a result, the radius is going to get smaller because the outermost energy level is not the valence electron level anymore. It's the core electron level. And the core electron level is closer to the nucleus. So you can see all the positively charged ions here have a smaller radius than that of the neutral atoms in and of themselves. And anions do the exact opposite. A full outer shell increases electron-electron repulsion, resulting in negatively charged ions having a greater atomic radius than that of its atom counterparts. I guess I should use the term ionic radius. When referring to cations and anions, they're ions, so it should be ionic radius, not atomic radius. But you get the idea here. Everything's still rooted in Coulomb's law. It's just that this trend happens to be the opposite of ionization energy. As we go down a group, the radius gets bigger. As we go left to right across a period, the radius gets smaller. Positively charged ions will have a smaller radius than their neutral counterparts, and negatively charged ions will have a larger radius than their neutral counterparts. So again, when we refer to the atomic radius, we're referring to the size of an atom. This decreases going left to right as the increasing number of protons in the nucleus increases Coulombic attractions of the valence electrons to the nucleus, and as those attractions increase, the electrons are pulled in closer, thus resulting in a smaller atomic radius. When we go down a group, the atomic radius increases as a result of the subsequent energy levels being further away from the nucleus, and as a result, you get a bigger atom as a result of that. Pretty straightforward. The next trend we're going to take a look at is electron affinity, and that is the attraction of an electron to a particular atom. Notice that that trend is very similar to that of ionization energy as well. Now, justification in Coulomb's law on this isn't quite as important. I would make sure that you know that elements on the right-hand side of the periodic table are going to be more likely to attract an electron than ones on the left side. And that's due to the fact that those atoms that are on the right-hand side, when they do take a charge, they take negative charges to reach that full octet. So as a result, you see higher ionization, you see higher electron affinity on the right-hand side of the periodic table. And again, just a general trend for you to go through and take a look at. The atoms on the left-hand side of the periodic table don't want to gain electrons, they want to lose them in order to get a full octet. So as a result, you see very low electron affinities. And again, electron affinity refers to the amount of energy released when an electron is gained. It simply refers to the likelihood of gaining an electron. This increase is growing across a period. As electrons are added, outer shells become more full and more stable. Noble gases tend to not want to gain electrons since they are already stable as well. The last trend we're going to take a look at is electronegativity, and it is just simply the tendency to attract shared pairs of electrons in a bond. Electrons are going to be pulled towards the atom in a bond that has the smaller atomic radius. Those electrons would have a greater attraction to the nucleus of the atom with the smaller radius because the distance between those electrons and that nucleus is smaller than another nucleus. And so the smaller nucleus will have the greater attraction, pull those electrons in closer, and as a result, you end up with an even or uneven sharing of electrons. In fact, you can have electronegativity values so great that you end up with an ionic bond, but that's something we're going to discuss in a later video. So if I look at the electronegativity values on the periodic table, the highest electronegativity values, again, just like ionization energy and electron affinity, are up and to the right on the periodic table. It follows the same trend as the smaller atomic radius. Electrons are going to be more attracted to an atom in a bond or within a bond that has the smaller radius because those electrons can get closer to the nucleus and there's more attraction there than, say, an atom with a larger radius. So here's what I'd like us to do. I'd like us to be able to account for the following utilizing some atomic principles. And this is one of those, rites of passage when you think about Coulomb's law in AP chemistry. You need to really be able to think about, on an atomic level, the attraction of those outermost electrons to the nucleus and use that as a justification for things like atomic radius and ionization energy. Less so much for electronegativity and electron affinity, which is why I primarily focus on ionization energy and atomic radius. So I want you to take a look at these two statements here and then do a little justification in regards to Coulomb's law. Again, claim, evidence, reasoning. State your claim. The radius of lithium is larger than that of beryllium. What's your evidence? Your evidence should be rooted in Coulomb's law, and then reason it out and justify why. Take a few moments with that, and I'll be with you in 1 moment. All right, so as we mentioned before, we're going to go ahead and take into account the following atomic principles So as I mentioned before, we're going to account for the following using atomic principles. Let's just start with the first one here. This is that the atomic radius of lithium is larger than that of beryllium. So start off with your claim. Lithium has a larger atomic radius than Be. So we look at lithium and beryllium, we find that they are in the same energy level. They're in the same period on the periodic table. So we're going to use the magnitude of charge of the nucleus as justification. Be has a greater magnitude of charge in the nucleus than that of lithium. This results in the valence electrons of beryllium being more attracted and closer to the nucleus. Oh, it's starting to rain. Than that of Li. This results in lithium having a larger radius than that of beryllium. So it's a bit hard to read, that's for sure, but I'll read this one more time. Lithium has a larger atomic radius than that of Be. Be has a greater magnitude of charge in the nucleus than that of Li. This results in the valence electrons of Be being more attracted and closer to the nucleus than that of Li. This results in Li having a larger radius than that of Be. So again, we're utilizing those principles, those atomic principles, looking at Coulomb's law, understanding that the magnitude of charge of the nucleus plays a role in how attracted those outermost electrons are to the nucleus. And as a result, that plays a role in things like ionization energy and atomic radius. So again, practice using your claim evidence reasoning, practice your justifications using Coulomb's law. So let's erase this. Our next question here asks us to analyze the fact that the second ionization energy of K is greater than the second ionization energy of Ca. So we're looking at successive ionization energies. Well, if I look at the location of potassium versus calcium on the periodic table, I find that potassium is in the first group, and as a result has one valence electron, whereas calcium is in group 2 and has 2 valence electrons. So the rationale here, and I'll use, again, claim evidence reasoning for this. I'm just going to start with this part down here as my claim. The second ionization energy of K is greater than the second ionization energy of Ca. This is due to K having 1 valence electron compared to Ca having 2 valence electrons. The second ionization of K removes a core electron, which is, let's rephrase that, which requires more energy to remove than the second valence electron of calcium. So again, to reiterate, this is due to potassium having 1 valence electron compared to calcium having 2. The second ionization of K removes a core electron, which requires more energy to remove than the second valence electron of Ca. Core electrons are much closer to the nucleus, and as a result, they're going to require more energy to remove them. So again, as you analyze these questions, and I wish I had the time to be able to go through every single type of question you're going to encounter, you just need to think about Coulomb's law as you go through and analyze these things. More attraction to the nucleus, higher ionization energy, smaller atomic radius. Again, I could go down the line here. There's so many things to think about. And this is one of the harder parts of AP chemistry, in my opinion, is thinking about how we go through and analyze each individual and specific situation. But again, think about Coulomb's law. Think about the distance between the nucleus and the electrons, the magnitude of the charge, and think about what's going to have a greater attraction. Remember, when we compare things in the same group, we're looking at the fact that the electrons are in different energy levels. When we compare things across the same period, we want to take into consideration that the magnitude of charge of the nucleus is going to be different as we go left to right on the periodic table. So again, just a couple things to think about as we wrap up our evaluation here. So again, thank you so much for watching. If you really liked it, feel free to like, subscribe, share. I'm happy to explore and try to give as much AP chemistry content as I possibly can. But again, thank you so much for all that you've done, and have a great day, and we will see you very, very soon in the next video. Bye-bye, everybody.